here, this here. All right, ladies and gentlemen, class recording has started. So, back on the second day of school, we introduced the big ideas of physical science. And one of those big ideas was matter and change. Anybody remember the gist of matter and change? I know I'm asking you to remember a long way back. Alex, go ahead. But, Kenny?
Yes, I'll
Marito? That's sort of a big idea. So, Alex, all the stuff that's in the universe goes through changes. It's still the same amount of stuff, just different forms, okay? We give that idea a name and we call it conservation. And when we say that something is conserved, it remains constant. That if you looked at the amount of a conserved quantity, it would be the same at the beginning of a situation as it is at the end of the situation. Matter is a conserved quantity. You may have heard of conservation of mass before, right? You can't create or destroy matter, meaning that if you measured the amount of matter that was there at the beginning of a situation, it would be the same as the amount of matter that was there at the end of a situation. Might look different, might be rearranged differently, but the amount is still there. And while matter is a conserved quantity, energy is also a conserved quantity. When we look at the total amount of energy in a closed system, it remains constant. Now notice, total in capital letters. Because on the first day of this unit, I showed you some slides and it had 6 different kinds of energy. And I told you that at some point during the year, we would talk in more detail about those 6 kinds of energy. But if we looked at all of them put together, we'd always have the same amount of energy. Now, in order to see that, in order to measure it, first we have to have something called a closed system, meaning that we can't put anything in or out, right? For example, if we were trying to show conservation of mass, and let's say, the whole class, we got on a big scale and we weighed whatever it was, okay? If we all rearranged ourselves, we should still weigh the same amount, unless we added 2 kids from a different class, right? Then that's not fair, right? We haven't closed the system. So when we talk about looking at these ideas, we have to first define what it is that we're looking at, then say, okay, does the energy in that remain the same, or does the mass in that remain the same? And again, like I kind of mentioned, right, when we talk about total energy, we have to talk about all kinds of energy, which is great and which is true. But some kinds of energy, like chemical energy and heat energy, they're just not as useful to us, or at least as easy to picture as some other kinds of energy, like, say, mechanical energy, which you've already written this slide down 3 times, and I think on your outline I wrote it down for you so you don't have to fill anything in, right? So mechanical energy, right? The energy associated with the motion and position of everyday objects, where an object is and what it's doing. And, like we've written down 3 times, mechanical energy is actually a combination of 3 different kinds of energy, right? Those 3 different kinds of energy are kinetic, potential gravitational, and potential elastic. And when we talk about the mechanical energy, we have to look at the sum of those 3. Okay, now that we've established some of those rules, okay, or some of those ideas, what we find is under certain situations, we can actually observe mechanical energy being conserved, or the conservation of mechanical energy. So it says, when there are only conservative forces acting on an object, mechanical energy is conserved. But when there are only conservative forces acting on an object, mechanical energy is conserved. So, your question that might come out of that statement is, What's a conservative force? Which is a good question. So let's talk about that. So conservative forces, sorry, did we not get that? So conservative forces. First, just based off the statement on the previous page, conservative forces do not change the amount of mechanical energy in a system. Okay? Now, you might say, well, wait a second. Back in the last section, we talked about work. And work is a change in energy. Yes? Okay. And work requires a force. So how can a force, like conservative force, not change the amount of energy in a system? Because there are two kinds of special forces out there. Those two forces are gravity and then elastic forces, like springs and rubber bands and bungee cords and trampolines and stuff like that. Okay? Yes, Shirley? Yeah, separate the two lines there for, to separate them. So. And what makes conservative forces special is that they don't change the actual amount of energy in a system, but they will convert one form of mechanical energy into something else, another form of mechanical energy, but without changing the total amount. So they kind of do work in that they convert energy from one form to another, but not in the way that it changes the total amount of energy. Let me go ahead.
Elastic forces are still B.
Yeah. A is gravity, E is elastic. So, conservative forces don't change the total amount of energy, but they will convert one form of energy into another form of energy. So they'll convert one form of mechanical into another form of mechanical. And if only conservative forces are acting on an object, mechanical energy is conserved, which you already wrote down. But mathematically, we represent that with this equation. MEI equals MEF, where ME is going to stand for mechanical energy. And so MEI is initial. And then MEF is going to be final. Right? So the mechanical energy that we start with, MEI, has to equal the mechanical energy that we end up with, MEF. So initial mechanical energy has to equal final mechanical energy, which is the idea of conservation. But remember, mechanical energy is actually a combination of three different kinds of energy. You have it written down on your paper, so you don't have to write it, okay? But, right, we have to look at the total. So KEI is initial kinetic energy, and KEF is final kinetic energy. Conservation doesn't say that KEI has to equal KEF. The amount of kinetic energy might change from beginning to end. But if we look at the sum of these three, the total of these three together, and the total of these three together, that number would remain the same. So we may see changes in individual amounts of energy, but the total has to remain constant. Good with that idea, at least to begin with. Okay, illustration. So, you guys have this whole situation on your outline, but it's much more dramatic if I present it in pieces like up here. So, we've been encountered with a situation, a dire situation, right? This lady trapped in a burning building. I guess I shouldn't stereotype like that, right? It's a person in a dress with a purse. It's probably a lady, but it could be a transvestite. I don't know. Anyway, I'm saying physical science does not discriminate. So, whether she's a lady or a transvestite, this will be the same. Sorry, let's go with crossdresser. How's that? Is that? Or a transvestite. Regardless, physical science does not discriminate. The answer would be the same. Right? So, all right. So here is this person up in a high floor of this burning building. And she decides that the situation is so dire that her only recourse is to jump out of this building. Okay? But she grabs her purse because, a lady's got to look respectable no matter what situation. Or a transvestite or a crossdresser. Always look respectable. So anyway, not it. That's kind of disrespectful, isn't it? So anyway, this person needs to look respectable. Anyway, so they're standing up on top of the ledge. Sorry, proper use of pronoun would be he, right? Because if we don't know, don't you use they? That would indicate that there are two of them, right? Anyway, so I think the proper use of the pronoun is he. I believe. We're not. This person. This person, before they decide to take that fateful step off the ledge, is very high up in the air, and therefore has a lot of potential energy, as you can see in this picture. But because this person has not started moving yet, their kinetic energy is at 0. Therefore, according to this picture, how much mechanical energy does this person have? 10,000 joules, right? Because what did you do to get the amount of mechanical energy? Add PE and KE, because that's what mechanical energy is. Yes, because remember, mechanical energy is a combination of those three kinds, right? Yeah, regardless of whether or not they're present or not. Yes, and that'll be important as we continue through this example. Okay, go ahead.
Would this be the same for whatever thing is jumping from the trampoline to the top of the building?
A little bit different, but the concept would be the same. So wait till we get to the end of this, and then I'll tell you how that would sort of change a little bit. Okay. All right. So as she jumps off the building, she starts to fall. As she's falling, as this person is falling, right? What's happening to the amount of potential energy that this person has? It decreases because she's getting lower, but as she's getting lower, what happens to her speed? Higher, and therefore, when she reaches the halfway point, right, if she has lost,
She lost her purse.
so don't worry, it's right with her. That's actually a physically accurate drawing. So, if this person has lost half of their potential energy, they will have gained just as much kinetic energy. Eddie, how much mechanical energy does this person have in the picture on the right? 10,000 joules, because we just what? Added potential and kinetic, we get 10,000. She continues to fall. Her potential energy continues to decrease, but she continues to go faster, so her kinetic energy is increasing. Until she reaches, right, this point. No, I told you have the whole picture, but it's much over.
I didn't realize.
No. So, but at the bottom, right, if we consider the point where this trampoline is to be height 0, she would have no more potential energy, but all of it would turn into kinetic. And right now, the total amount of mechanical energy she has is still 10,000 joules. Okay? So, what? Yes. Well, let's talk. We can talk about that in just a second. Okay? All right. So, one, at the risk of getting us off topic for 1 minute, okay, maybe less than a minute. All right. This picture picture, the bottom right here, reminds me of two things whenever I see it every week. The first thing it reminds me of is the best day of elementary school gym class, right? The parachute, right? You play popcorn with that bad boy, right? You throw the Nerf balls in, and then everybody like lifts it high up, and then you all go inside and sit on the mushroom.
I want to buy one. I'll buy one. We can do it inside.
Those were the days, right?
Can we get that for like a lab or something?
No. See, now that your life has progressed to this, all you can do is talk about it. Reminisce about the good old days. So the second thing that it makes me think of is that, so you see this a lot, like in like old movies when like people were trapped in the tree or where to go, right? The firemen just catch them, right? Sorry, fire people.
I like
So,
that.
fire people? I mean, you know. So, like the fire people just catch this person, right? But now, if this happened like nowadays, we would just get the big extension ladder deal and like put the little, the little basket right next to the window and say, hey, just step out here and we'll, But it makes me think that at the fire station, they still have one of these, like up in the attic or something. And then every spring they're like, you gotta get rid of this thing. And someone's like, no, what if the ladder's broken, right? Like, can't get rid of that, right? You have to be prepared. What? Maybe. Just practice. We're practicing. So, now, so right next to, or right above, or I guess right next to this picture here, right? There is a question. Is mechanical energy conserved in this situation? So the answer in this case is yes. There's two ways you can go with the next part, why or why not. The first way you can go is, if we look at the sum of kinetic and potential, what do we keep coming up with the whole time? 10,000. So the sum of kinetic and potential never changes. So that's conservation. The second way we can look at it is, in this simplistic example, or simplification of this example, what would be the only force that is acting on this lady as she falls out of the window? Gravity. And we just learned that gravity is a conservative force, so it doesn't change the total amount of mechanical energy, but it just converts potential into kinetic. Okay? So either way would be a sufficient way to answer that question. Okay? Yes, Alex?
That's for basis with
Yep.
like how we're holding it.
Yep.
It wouldn't be quite 10,000 because it's not like registering.
Now, we talk about potential energy as being a height from the ground, okay? But really, potential energy is defined as some height that we consider to be zero, okay?
So we consider it like
right, we consider that to be the lowest point. It's not actually the ground. But one thing that gets much more detailed and intricate with our analysis of the situation. The ground a lot of times is the easiest thing to pick zero, but we could actually pick any spot we want to be zero, and then it would be okay. But for your purposes, we'll just call the ground zero, and that makes your life easier.
Wait, but what if you're, so it's a lady or a man or whatever
Yeah.
is that 10,000 from where she's gonna be?
Yes. Yeah. Whatever height we decide. Okay, this is zero height. Okay. Valentina, go ahead.
So like the ground or whatever you're landing on is always zero because like anything is
Technically, although, like in this case, so if we called this ground zero, we're not actually at sea level, right? We're a little above sea level. But our analysis of the problem would be just the same whether we called this ground zero or whether we called it like 100 meters above sea level or however far we are above sea level. What actually happens in the problem, potential goes down, kinetic goes up by exactly the same amount, regardless of whether we call the ground zero or not. Okay?
Okay, this is like a weird question, but what happens if like we decided ground zero would be like the third floor of the building?
That's okay.
Then what would happen if she keeps on falling down the side?
Then she would end up with negative potential energy. And then when we add them together, guess what we end up with? Same amount.
Okay.
All right, good there? Okay, so right to the right of your graph there, right? To the right of this figure, there is a picture that, or there's a set of XY axis, okay? So let's grab this here, and put it here, and let's take a look at it. Whoa, that's way too big. Sorry, let me do this. That'll look good on the recording.
No, it doesn't show on here.
Okay. All right, so let's make this a little smaller because it's way too big right now. All right, so in this picture, if we were to look at the energy values of the different kinetic and potential, first, what's going to happen to kinetic? It's going to go up. However, as we learned earlier this week, right, the formula for kinetic energy looks like what? 1/2 mv squared. When we have a squared term in an equation, what does it look like on a graph? It looks like a parabola. So, in this case, what? Does that look familiar? This is this is only half of a parabola.
Does it go all the way?
No, it would actually go this way, okay? But here, right, the x or the y-axis, that would be times 0. So if our parabola went over here onto this side, that would be negative time, and that doesn't work. You right? Okay.
That's
Okay.
scary.
But the potential energy needs to go down,
It looks like a fish.
but it has to mirror the kinetic energy going up.
It's like Christian.
Kind of. But if I added this line,
What's that? What is that?
that would be the mechanical energy, because what happens to it? Right? So this is ME, right? This is KE, and this is PEG. Okay? All right, so tomorrow we will look at what happens when there's something other than a conservative force acting on an object.
Is there